a computation where we might be tempted to use something that looks sort of like what we're trying to compute in terms of using properties of logarithms. Yeah, that's understood to be log base 10, although the base is not really important for this problem. So the famous result, it's easy to prove using the laws of exponents, is this. Okay, that's equal to the log of A minus B, right? Log of A minus the log of B. Right? Again, this is what we might want to do, but that is not the form. We have a single logarithm which encapsulates a quotient, and by laws of exponents you get this. Just the same reason you subtract exponents, when you have a quotient. Okay, that's not what we have. Okay, so we can't use this. We have to resort to the definition. So what we're going to do is set the numerator equal to the integer, or the real number A, and the denominator equal to the real number B, okay, is what that's intended to do. And remember, every logarithmic statement has a corresponding exponential statement, and so that follows right here. Remember, a logarithm is an exponent, and so here A appears as an exponent as well as B, okay? So we converted this statement right here into a pair of exponential statements, which are fairly easy to manipulate. We're just going to take the product. You can multiply equals, right? And so we get this statement right here, and this would, laws of exponents right here would give us 10 to the A plus B, little a. Now, of course, you recognize this as the difference of two squares. So this would be equal to 33 squared minus 8. So y'all, this would be minus 64 times 17. Right, folks? Again, you square 8, you get 64. You square the square root of something, you get the something. And this happens to be 33 times 33 is not too hard to compute mentally. This one just requires that you just do it. It's 2-column multiplication. It's not too hard. It's just, but I'm not going to take time to do that for you guys. It's 1088. Okay, so that's equal to 1. So now we can work our way. The only way this can be true, folks, in other words, we have 10A plus B is equal to 1, right? Let me just write it down under here. We have 10 Now some of you might be tempted to take another logarithm here, but the only way that this statement can be true is if A plus B is equal to 0, right? Right? Any base raised to the 0 power is just 1. And that's a weird looking 0. My apologies for that. So that tells us that A equals to negative B. Yeah, and another way of thinking of that is A over B equals negative 1. Okay, y'all, that's supposed to be a B right there. A divided by B. Let me take the time to erase that, make it neater for you. Okay, so we come back and make this thing activate again. So this will be B. A over B is equal to negative 1. God, it's doing that. I need a better way of doing this. I've been doing the mouse all of these years. I need a better system. I like what I'm doing, but I've never learned to use whatever it is that other people are using, you know. So this is A over B is equal to negative 1. But guess what? That's what this is right here. So our answer is negative 1. Isn't that nice? Okay. So the answer to the question is that we did the computation and we got negative 1. And it took a special sort of circumstance, didn't it? It doesn't look like, but this is the general form right here, and that's a separate video probably. But this is really, anytime you have something in this form, you're always going to get -1 out of it. Okay? It's just not evident numerically that it's in this form, right? It's kind of interesting. This is a special case. In the general case is more above board, if you will, and it all works out very nicely, and you would get 1 out of it the same sort of way, and you would get 10 raised to the a plus b is equal to 1, and so on and so forth. But this is an example of these are what they call additive inverses. A plus b are additive inverses. In the quotient of additive inverses has to be -1 all the way back from middle school. Okay, folks, that is all.